Hi everyone, my name is Piruz Barkhordar. I'm the Protection Division Manager in ETAP. The topics of today's webinar would be objectives of motor protection. We'll go over the common motor protection types, discuss about normal and abnormal conditions, and how we can represent them as a landmark or time current curves. We discuss about nameplate of the motor to make sure that you have proper understanding of how to extract the data from the nameplate and represent it or simulate it in the time current curves. Discuss about overcurrent protection concept and criteria. Go through the typical schemes for motor protection based on voltage and the size, and provide you with some suggestion or guidelines for applying the settings based on the standards. And at the end, we'll go over the auto evaluation application, which is a new powerful tool we added in ETAP version 14. So this is something that you can review the full capability in a separate webinar, but in this webinar we will go over the motor protection in specific. Okay, let's start then. The objectives of the motor protection is not different than other types of apparatus or equipment protection. The first objective, as usual, is the human safety, prevent the injury and fatality to the personnel who's working on the equipment. And the second objective is protection of the equipment itself, meaning permit or allow normal operation of the equipment, in this case in the motor, and make sure that your protective devices have no interference with the operating characteristic of your motor. At the same time, we want to make sure if there is any abnormal condition, if there is a fault, overload, short circuit, any excessive current, when we are talking about the overcurrent protection, we want to make sure that we can detect that specific event or abnormal condition and isolate their equipment from the rest of the system and avoid any damage to the equipment. At the end, reliability and the cost is a target. Typically, what we want to have is to achieve maximum reliability for protection at minimal cost. This is kind of art, but at the end you need to make a compromise between the protection cost and a machine operation value. As we said in this webinar, our focus would be on the overcurrent protection, or as they call it, inverse definite minimum time, or IDMT protection. And overcurrent protection typically is split in two parts, overcurrent and the differential. We'll mainly focus on the overcurrent, and we'll have a brief review of the differential, which would be summation of the currents. Other types of the protection would be voltage protection for under, over, or unbalanced voltage, and single phasing, which would not be part of this webinar. You can also have RTD, resistant temperature detector, limitation number of starts and time in between, loss of load protection, reverse spin, surge protection, breaker failure, distant protection, and so forth for motor. This is just for your information that naturally in such a short period of time we have for this webinar, we won't be able to cover them all. The only thing you should know is when we are talking about the motor protection and the difference between induction and synchronous motor protection, the main difference is excitation protection. Naturally, for synchronous motor, you need to have excitation protection, and excitation protection is split in two parts: out of step or loss of synchronous with the connected network, and loss of the field supply protection. These are the two additional fields of protection which synchronous motor would have on top of induction. As we said, overcurrent protection criteria would be based on permitting the normal starting and running condition of the motor. This means we should permit maximum permitted current and working condition of the motor. This working condition means temperature, the cooling media that you have, elevation, and etc. For the protection, we should protect the motor against any abnormal overcurrent condition. These abnormal overcurrent conditions are represented by excessive operating and true fault current, which can be caused by design, installation, ambient temperature, or incident during the running or starting of the motor itself. We represent these normal and abnormal conditions on a log-log TCC curve. the vertical axis is the time and the horizontal axis is the current. So what you would have as the normal operating condition would be an starting curve for the motor, which would start with the magnetizing inrush current. Typically this magnitude would be 1.6 times of the lock rotor current. Then it would come and reach to the acceleration time when the motor has actually started and it's reaching the full load current. As can be seen in this slide, the induction motor operating characteristic has a dependency on the voltage. As it's been discussed in previous part of the webinar, the acceleration torque of the motor depends on the voltage. This means the motor starting curve has a linear relationship to the square of the voltage. This means that if you have 10% voltage drop, or your voltage is at 90% of nominal voltage, the actual starting torque of the motor would be reduced by a square of this amount, which would be 81%, equivalent to 19% torque drop. Drop in the starting torque means the motor would have less acceleration torque because the load torque remains the same. So the starting time for the lower voltage would be higher, as you can see, or longer. You should know that during the starting, motor can be represented or estimated as constant impedance, meaning if you reduce the voltage, the current would be reduced linearly. And as you can see, if you reduce the voltage, the magnitude of the current will be shifted to the left, but the acceleration time would be longer. So as a general practice for representing of normal operation mode of motor, you can plot all of these three voltage curves, but typically the 100%, 80% is the most common type that is used because in most of the cases you won't have over voltage at the terminal of the motor. The abnormal condition of the motor is caused by internal and external faults. External faults would be overloading during the running, overloading during the starting, or stall, or jam, which means the shaft of the motor is locked because of the load and cannot rotate. It could be caused by phase or ground faults on motor feeder, or under voltage or unbalanced voltage or unbalanced loading. The internal faults of the motor are typically the interwinding faults, or between the winding and the body of the motor, which would be the ground faults. These external and internal faults of motor would cause additional losses through the motor, so the motor would be exposed to excessive thermal energy caused by the current and with linear relationship to the square of the current. So the current by itself and any unbalance in the current in the three phases together with the starting current of the motor would add to the total thermal energy that the motor can withstand. The capacity or withstand or thermal limit of the motor can be represented by a bucket. This bucket has a limit representing the motor thermal capacity or thermal limit, and this bucket will be filled by different sources of the thermal energy, which would be the motor losses, the I squared T in the stator. It would be caused by the unbalanced current between the three phases. Depending on the ambient temperature, naturally the cooling of the motor provided by the fan could have different impact on reducing the thermal energy capability. So all together would give you a thermal energy capacity or thermal limit curve. These thermal limit curves are represented on the TCC curve as stator and rotor plot curves. As you can see, these curves, this is for the rotor and this is for the stator. This curve have both hot and cold. The meaning of the hot is the motor is already started and you're restarting it again, or the motor was running and started again and comes into the running mode again. To plot these curves, we need the information from the manufacturer, and if such information is not available with the manufacturer, especially in relation to the operating curve, another option is to have the nameplate data of the motor if it is an existing motor. So the protection engineer need to have a proper understanding of the nameplate data and how it can be translated into motor characteristic curves. This is a sample of a motor nameplate based on NEMA or CSA, and as you can see, the information typically contains the FLA, the full load current that we showed on the TCC. This full load current would be at the nominal voltage, and this voltage would produce the nominal torque of the motor. Number of phases, total horsepower or the mechanical power output, type of the duty, frequency and RPM are other parts of the information you can typically find in this kind of nameplate. Another important information for plotting of the motor starting curve is the code letter, or as we call it, lock rotor kVA per horsepower code letter. This code letter, which you can see here as code G, is representing for each horsepower of the motor what would be the total kVA of the lock rotor current. So this multiplication factor under this table, based on the code letters which are starting from A and ending to V, are representing the total lock rotor kVA. From this kVA you can find or calculate the lock rotor current naturally, and then plot or calculate the LRC of the motor. Other parameters of the motor that you can find on the nameplate is the design letter. In this case, this is design B, which is representing the torque versus speed characteristic. For the protection engineer, the impact of the operating conditions, meaning the temperature, altitude, and the duty of the motor, is important. Because as you can see in a sample table on the right, for 40 degrees centigrade of ambient temperature and 1000 meter altitude, which is equivalent to 3000 feet, the multiplication factor to the full load current of the motor would be 1. This multiplication factor can be applied to the horsepower as well. But if you increase the altitude or increase the temperature, you would see that the multiplication factor becomes less than 1. This means that the motor mechanical power output or the full load current that you can take out of this motor will be reduced, and this needs to be considered in overload protection of the motor. Service factor is also another important parameter in overload protection, especially in motors which are made based on NEMA or CSA standard. Typically the IEC motors have a service factor of 1. This multiplication factor is applied to the rated horsepower, meaning it will be applied to the full load current of the motor too. So for overload protection, you need to be aware of this service factor and naturally permit the overloading of the motor based on service factor and adjust your overload protective devices accordingly. Another important parameter on the nameplate of a motor is the insulation class of the motor. Based on NEMA, you can have 4 classes of the motor, which is representing the maximum allowed temperature. Maximum allowed temperature is representing how much overload you can have for this motor depending on the ambient temperature. This temperature represents the hot spot of the winding, and when you're looking at class A, it means it has maximum total 150 degrees centigrade maximum hotspot temperature. This 105 is calculated based on 40 degrees centigrade of the ambient temperature or 104 Fahrenheit. An additional 65 centigrade for the temperature rise for the motor. So depending on the insulation class of the motor, the capability of the motor to withstand the overload would be different. If you look at the insulation lifetime versus the operating condition, a common rule of thumb which is represented by this curve is for every 5% in addition of the overload current. The IN is representing the maximum full load current that the motor can withstand based on insulation and service factor. So if you have 5% over that allowed current or 10 degrees centigrade increase in the temperature of the winding, the lifetime of the insulation will be reduced by half or 50%. So you can see it would have a huge impact. So we want to make sure when we are protecting the motor for the overload, we are not allowing for such additional overloading conditions and reduce the insulation lifetime of the motor. The IEEE standard has similar insulation class, but they define 10 degrees margin on top of what we have in NEMA. They don't have class A, instead they have class FB, which is combination of class F and class B. After knowing the operating characteristic of the motor based on the nameplate or manufacturer provided data, we can plot the starting and running curve of the motor. The thermal limit curve of the motors typically need to be provided by the manufacturer, and for the smaller size of the motors it is hard to find. But at least you may predict or guess this stall point, these two damage points, which is the maximum withstand capability or thermal limit capability of the motor at locked rotor current. For the NEMA motors, typically this is 20 seconds. And for the IEC motors, this is typically 10 seconds. You need to verify this information or that with the manufacturer, but if there is no other source, that could be used as the typical value. But at the end, the time current curve of your protective devices should be plotted and set in a manner to have a margin between the TCC of your protective device and operating curve of your motor, and interrupt the fault current beyond the locked rotor current at the minimum time, and at the same time reduce the duration of the fault for any current between the full load, nominal permitted full load current of the motor, up to maximum locked rotor current beyond the withstand capabilities. So the time current curve of the device should be to the right and above of normal operating curves, and should be to the left and below of the thermal limit curves, and at the same time it should limit the magnitude and duration of fault currents, as you can see here. Typical protective devices that can be used for overcurrent protection of the motor. The first item is the switching devices such as starter or contactor, or disconnect switches or breaker. The next item is overload relay, which is having a thermal or bimetal heater if it is thermal heating relay. If it is electronic, then it would have protection elements such as thermal, which is resembling or representing the same behavior of the thermal. Additional, it may have acceleration, jam, ground, neutral, negative sequence, or unbalanced current as well. Another type of the relay which is used for protection of the motor is called the overcurrent relay. The protection element in this type of relays is phase, ground, neutral, and negative sequence, but you can find relays which is a mix and match of both. You can have overload, or you can call them overload or overcurrent, or the mix of both. It doesn't matter. What is important is being able to present the protection element or the functionality of the relay properly. Differential relay is another type of the protective device that is commonly used for larger size of the motors, and typically is protecting the motor for the internal faults. Fuse, medium voltage or low voltage, and low voltage breakers are the most common type of the protective devices you can find in the low voltage system. Protection scheme for the motor depends on multiple parameters. The most important parameter or factor for design of the protection scheme is the motor size and voltage. Naturally, the larger size that you have, the larger voltage you would have for the motor. It means that the investment for the equipment is higher and justifies the higher investment for the protection of it as well. This is a sample table to tell you what would be the typical size of the motor based on the voltage. As you can see, for 460 volt, which is in US or North America, up to 500 horsepower motors can be installed on 480 volt, which is the nominal voltage. This is the motor voltage nominal, and this is the system nominal voltage. But practically the Size of the motor for the low voltage is limited to 250 unless there is a requirement or necessity or justification for it. Sizes larger than 250, 300, 350 can typically fall into the medium voltage category. And as you can see, for 250 to 2000 you can have medium voltage, 250 to 3000 you can have higher medium voltage, and above 2000 horsepower you go to 13.8 kV. This is the suggested one. This selection is based on multiple factors. As you can see, it is motor characteristics, availability of the protective device for that amount of the current, the type of the application, maintenance, and so forth. So one of the major items, as I mentioned in the beginning, is the size and voltage to predict the typical protection scheme for this motor. If you like to have further information regarding this typical scheme or suggested scheme for protection of the motor, this standard IEEE P3004 is a good one for reference. Also, the C3796 guide for AC motor protection is a good reference for motor protection. All of these standards needs to be reviewed and used as the reference for the motor protection depending on which part of your world you are and who's the jurisdiction having authority for the installed equipment. So this standard needs to be reviewed, need to be known, and set the setting based on this standard unless you have a justification not to follow. Typical schemes for the motor. The low voltage motor protection is typically pre-engineered. It means that you have a combination of protective devices already designed for a specific size of a motor. This comes as overload and short circuit protection together. Most common type is for the low voltage devices is a combination of overload protection. It could be overload heater or overload relay, and breaker or motor circuit protector, which is an instantaneous or magnetic type of the breaker. As can be represented here, you would have an overload and magnetic section in this area. If you refer to the IEEE C3796, they have a table for suggested scheme of protection for low voltage. And as you can see, it can come up with the overload, as we said, a starter or contactor, then a switching device with the backup or fault protection. This fault protection could be fuse or could be a magnetic device. For ground fault protection, the standard is suggesting a core balance CT to measure the residual current directly from the unbalanced current of the three phases. This is the low voltage motor protection schemes that typically you can find industry, and it is also suggested by different standards. Typically they are combining overload relay, starter, and a short circuit protection element. This short circuit protection element could be an MCP, motor circuit protector, or could be a thermal magnetic breaker. This thermal magnetic breaker, if the withstand fault current of the breaker is not sufficient, could be supported by a backup protection like a fuse. If you don't need breaker in this case, you can replace it with a fuse and then have a switch upstream of the fuse. Naturally, as you know, the difference between these two is the restoration time. For the fuse, if it's blown, you need to replace it. For the breaker, you may switch it on after resolving or removing the fault. Another cheap and common type of the protection is overload, starter or contactor, and MCP, motor circuit protector, which is the thermal magnetic curves. Or you can use a single molded case circuit breaker or power circuit breaker for protection of the motor all at the same time. Another option is to use the relay for protection of the motor. In this case, you would have CTs for the phase and for the ground together with the starter, and your phase and ground protection element would send the signal for opening of the breaker in case of a fault. This is a low voltage breaker which can have a shunt trip initiated or tripped by these two relays. Let me show you the low voltage motor protection schemes in ETAP. These are the same schemes that I have showed you before. Let's have a look at the time current curves of each. The first one, as you can see, is the low voltage motor with the overload relay and molded case circuit breaker with the fuse backup. As you can see, the combination of these curves should be to the right and above of the time current curve of the motor, and to the left and below of the thermal limit curves of the motor. The second one is a combination of fuse and overload. As you can see, the fuse is used for the short circuit protection and overload is used for the overload protection with the same concept, combination of overload and MCP. A single breaker with the solid state trip unit for protection of both operating and thermal limit curves of the motor as one. This is a relay applied to the voltage. It is sending the trip signal to the low voltage breaker, possibly a power circuit breaker. Again, overload protection and the short circuit protection. Now that we have reviewed the typical schemes for low voltage motor protection, let's see how we can apply the proper settings to each of these protective devices. Overload relays, either electronic or bimetal or thermal, based on National Electrical Code Article 432, for continuous duty motors, the maximum pickup setting for the FLA should be 125%. If the motor does not have a temperature rise over 40 degrees C, you can use the same maximum pickup for such overload as well. But if the service factor is less than 1.15, then the maximum pickup setting for such motors based on the National Electrical Code or for the NEMA standard motors would be 115%. The overload relays are typically combined with starters and have a class for the duration of the trip time. Based on NEMA ICS 2 class definition, a class 20 overload relay motor would trip the current of 600% of current rating in less than 20 seconds. There are other classes like class 10, class 15, class 30, and even class 35 for the electronic overload relays as well. But class 20 is typically used for NEMA or North American manufactured motors, and class 10 is typically used for the IEEE World or IEEE standard manufactured motors. Same class for the IEC. The definition of the delay time or duration of withstand of the current to interrupt it is a little bit different. Based on IC 6947, the class definition for 20 is a current which is rising from the cold status to 7.2 times of the rated current, and the duration for the interruption could be something between 6 seconds to 20 seconds, as can be seen here. For class 10, this would be between 4 to 10 seconds. And also the manufacturers provide you with the tables to give you a combination of the size for the starters, fuses, contactors, breakers for such low voltage combination. This is a sample for NEMA, which is based on different motor horsepower, and it would give you the 460 volt NEC full load current and represent the starter size, conductor, and so forth. So this table can be used for sizing your protective devices as well. Fuses and the classes of the fuse. In the UL or CSA or ANSE or Mexico classes, the typical fuse classes which are used for motor protection are RK1, RK5, which are current limiting fuses. Most typical type of the fuse which is used for the motor protection is the J type. You can also use CC and L. The L type is typically for large size of the motors or currents above 600 amps. These fuses can be made or used in two different types. They could be fast acting or standard acting, or time delayed or slow speed, which means the opening time for the fuse would be 10 seconds at 500% of the current rating. For the IEC, we have a different standard, 6269. The IEC is representing the fuse by two letter code. The first letter is representing either it's a short circuit protection only or it is a general purpose protection. And the second letter is representing the most practical application. So D is representing fuse which would be equivalent to North American fuses for motor circuits, UL248 fuses, and the G for general purpose, and M is for the motor. So this means for the IC fuses, if we want to use any fuse, it should be typically AD, AG, or AM, right? Or G with the combination of these if you cannot find any equivalent one. Typically cannot provide a full range of overload protection. Newly made fuses have a special characteristic that to some extent provide the full load current or overload protection as well. But typically the fuses are combined with the overload protection, and the fuse itself is used for the phase and ground fault protection. If this is the case, the National Electrical Code, the NEC, Article 43052 and IEEE C3796 suggest the following rating for the fuse. This is the maximum rating for the fuse. So for non-time delay fuses, the maximum is typically 300% of the FLA of the motor. And for larger size of the fuses, above 600, this would be 400%. The dual element or time delayed fuses, typically this maximum is 175%. Looking at the suggested setting for the low voltage breakers and sizing the breaker for the motor protection, if this fuse is sized for the fault protection, not for the overload protection, then you can size the fuse up to 250% of the FLA. Typical industry practice is 150% of the FLA. The instantaneous strip breaker can have up to 800 to 1300% of the FLA, but it can go up to 1700% depending on the design of the motor. But once you have the proof of the study that this motor cannot be started, naturally this percentage could be overloaded, and you can show that you need to higher instantaneous setting to protect your motor. Use your breaker for full protection of the motor, not only the fault but also the overload protection. Then the typical application guidelines for adjustment of the setting is 115 to 140% of FLA of the motor based on service factor. And instantaneous pickup is typically 175 to 200% of the LRC. The time current curve of the motor, as can be seen here, should be above the motor starting operating curve and below the thermal limit curves, as it was explained before. For the medium voltage motors, The IEEE C3796 provides you with the table and typical protection scheme. Combination would be different types of relays to sense the current, phase, and ground, and unbalanced current, and also a differential together with the fault detection inside of the motor winding itself. All of these protection elements are sending the trip signal to a high voltage circuit breaker, or disconnecting or interrupting the motor in case of the fault. You can also have voltage relays for under voltage or over voltage or unbalanced voltage as well. Let me show you these schemes in ETAP. As you can see, there is a combination of relays, starter or breaker with short circuit protection if you have a starter like a fuse, or if it's a breaker, naturally you won't need a fuse. Typically you would have phase and ground CTs, and depending on the size and the operation value of the motor, the functionality of these relays would be different. So let's review some of them. This is the combination of relay. This relay has multiple function. If you see the function, this relay has phase, neutral, ground, and negative sequence that can be used for protection of this motor. The next one is an overcurrent relay. This could be electromechanical relay with the function for the phase and ground, which is sensing the phase and ground and sending the tripping signal to the breaker. If I switch to the ground, that would be the functionality of the. Let me show you the third scheme, which really has everything. It has voltage protection for the over voltage and under voltage, and he has the function for the negative sequence, as the function for the overload, as you can see, as the function for the jam, and this is the thermal characteristic of the motor, the hot stator thermal limit curve, and this is for the acceleration of the motor. Different types of relays have the role of protection in medium voltage motors. Below is the typical application of different protection elements for relays. The 49, as can be seen, is typically used for the overload protection and start failure. The 51, time over current, can be used as an alternative for the overload protection, especially with the new microprocessor relays. It can also protect the stator, rotor, and stall landmark or the damage point. The IOC or 50 functional protection element is used for the short circuit, and depending on the type of the CT you are connecting to the motor and location of the CT, you can use the ground and neutral with a combination of 51G, 50G, or 51N or 50N for detecting of the earth or ground faults. Let's have a look at the suggested pickup for fault protection by the TOC or 51. The overload protection of the 51 is similar to the overload relay, so we don't need to repeat it again. But for the fault protection, typical range of setting for the pickup would be 150 to 175% of FLA of the motor. The delay time for lock rotor protection is suggested to be between 2 to 5 seconds above the acceleration time of motor at rated voltage, or 10 to 20% time margin above starting time. For the phase unbalance or unbalanced current, the negative sequence current pickup is typically set at 15% of the nominal FLA of the motor, with the delay to between 2 to 5 seconds. The ground pickup of the overcurrent relay depends on grounding connection, and you set it up in a manner to avoid false tripping due to unbalanced starting currents. This unbalanced starting current depends on the type of the measurement you have for the residual current. If you have core balance CT or individual phase CT residually connected outside of the relay, and in any rate you need to set it up at minimum possible setting with minimum delay, but avoiding any false tripping due to these unbalanced currents. As we discussed for the ground function, one of the parameters defining the setting for the pickup is type of the measurement for the residual current or the ground current. The suggested approach for measuring of such current is through core balance CT or toroidal or donut CT. The advantage of this CT is you can even have a sensitive ground relay for measurement of the ground fault, because there would be one core which would measure the summation of the current passing through the three phases. But if you look at the other alternative, which would be residually connection of the phase CTs, this would typically lead to some errors. These errors are caused by dissimilarities in burdens of each phase and unsymmetrical saturation for each type of CT, even if they are same model, same type. So you cannot guarantee that they are ideally the same. This type of connection typically cannot provide the sensitive ground fault for protection of the motor. Differential protection relays are used for internal fault detection of the motors. As can be seen in this slide, the connection of this relay to the CTs and the windings of the motor could have two alternatives. In the first alternative, you are using three core balance CT and passing through this CT the incoming and outgoing wires connected to sides of each of the windings of the motor. In the second alternative, the differential has 6 CTs. 3 of them is connected to incoming feeders of the motors at the terminals, and then 3 of them would be connected at the other end before connection together or connecting to the ground. Now let's have a look at the capability of auto evaluation for motor protection. In ETAP, as I mentioned before, starting from ETAP version 14, we have added a new feature which is called Star Auto Evaluation. What it does, it is simply evaluates any existing setting for any type of apparatus, including the motor, like these low voltage motors that I showed you before, and provides you with the graphical and tabular format of the result, and you can adjust this setting on the fly. Instead of explaining, let me show you how it works. Select all of the motors in a single click or one by one, whatever you choose. So in this case, I've selected 5 motors. When I select these motors, you can see on the right, the star auto evaluation button becomes enabled. So I simply press this button. I've already selected the name for the report, which is auto evaluation, and then the program would create a tabular format with a graphical presentation of result for motor protection. And for each one of them, it would tell you what are the areas of the concern. This setting could be as found setting at the site, or this setting could be the initial setting that you can pick up by selection of any protected device model from ETAP library. So starting from the top, you see for this specific motor, the program has highlighted the areas of protection problem. As you can see, for motor protection, we provide you with the motor ID as the name of the zone, the device ID or the protected devices which are protecting the motors, type of these devices. Then we evaluate the motor protection versus pickup limit, pickup range. We evaluate it versus the FLA, full load current of the motor, the acceleration time, lock rotor current, and all of the damage curve, which would be rotor damage curve or stall times or stator damage curve, all of them. So in this case, the program has showed you a red sign as an alert, and it is telling you magnetic tripped pickup, which is 40-50 amps, is above maximum limit of 3110, which is 200% of the LRC. So the program is intelligent enough to figure out what is the LRC, and this 200% comes from the rule book that you can customize and edit as you wish. This would be the protection for the motor. And as you can see, for different types of protective devices, including the low voltage breakers, such as thermal, magnetic, or magnetic, we have set the maximum to 200%. This is industry practice. You can increase it up to 250 as well. So that's why it has highlighted this area. You can also see that for motor 2, we have problem with the pickup limit, acceleration time, and lock rotor current, and all of this is because of the combination of the fuse and overload that we have. So to fix the problem, for instance, you can simply from the graphical view adjust the fuse, and as soon as you adjust it, the program would let you know if everything is okay for the pickup, FLA, acceleration, lock rotor current, and the damage curve. And notice that the program is also intelligent enough to combine the two curves and make sure the combination of the two is representing the lowest curve of the combine. We can do the same thing for other ones. For IM3, you see we don't have any problem because it's perfectly protecting the motor in respect to the starting and running characteristic. For IM4, we see the pickup of the breaker is not properly set, and also the long time delay is not properly set. If you have a larger project and you don't want to update the setting and the evaluation results on the fly because it may take time, you may have selected a lot of apparatus for the protection evaluation. What you can do is you can turn off the auto evaluation and then do all of the correction yourself and then run the evaluation after. So I can bring the pickup to the right of the motor, bring the time delay to this area. I have problem with the instantaneous as well because the pickup is above the maximum limit. Let's see if I can correct this. And you can see if I'm accounting for the 100% motor voltage, then this does not work. As you can see, this is 100% of the voltage and this is 80%. So it would overlap. So I should compromise, either overlap with the 100%, assuming that I wouldn't have 100% startup voltage, and shift it to the left, or leave it as it is to the right. Let's have a look at the IM5.2. In here, the program is showing you the problem you have with the acceleration lock rotor current because of the overlap of the TOC over these two. So if I move it up, then I look at the curve and see it should be fine. But as you can see, the left side is not updated. The tabular format is not updated because you have asked the program to don't run the evaluation till you're done. And notice that the evaluation turns into orange, meaning that the evaluation result for the tabular section and the graphical section are not synced, and you need to run it. So as soon as I press this button, then you would see everything based on what we have set. And as I said, for the instantaneous, you have no other choice. You have to live with it. We are fine with IM3. We are fine with IM2. With IM1, we need to adjust the setting for the instantaneous, but that's what is mentioning for the instantaneous. We can do that, but you see the magnitude of the value is 13600 and still it is above 3110. So this magnetic setting has discrete setting, so you can only go between 7 or 8, and if you select 7, again you would overlap with the, and still it is high. So you should figure out how you can solve this problem or test it at the site to see if it is acceptable. Let me show you the rule book also. The rule book that we have for star auto evaluation, we have two different rule books, one for the ANSI and one for the IEC. Let me show you the ANSI one. In the rule book, we have 4 different elements, and I showed you the induction motor. In the rule book, what you can do is to evaluate the threshold or the pickup of all of your protective devices based on the landmarks, which are FLA or lock rotor current of the motor. You can also do the protection evaluation, which is comparison of the time current curve of your protective devices with the thermal limit curves of the motor. We following the NEC if you wish to. So the NEC is already supported NEC 43032, the article which I discussed for the overload protection, and the range that I showed you in the slides is already built into the software. If you have other rules for yourself, you can customize and change it if you wish. These values, this percentage could be customized. We also have the support for the higher settings based on NEC. If the exact setting does not match the proper protection or pickup, you can go with one level higher if it is acceptable by NEC. The other three checkboxes are supporting the proximity check. These are the checking the time and current margin between the time current curve of the protective devices and the damage curve or the thermal limit curves of the motors. At the end, we can also show you the reports for these motors. If I look at the report manager, I have a report for evaluation, and if I press OK, you can see the results in an Excel sheet. In this case, we have selected only motor. This is a summary of the evaluation result, protection evaluation result, and this is exactly the same table that we have seen in the tabular part in Excel sheet format. So if you like, you can customize it, you can edit it and add your comments, add another column for comments if you wish to. For reporting purposes, what you can do is you can also grab a graphical screen capture of the time current curve as well. You can simply press this button, then left click on the TCC, then the program would grab a screenshot of this graphical portion that you can paste it in any third-party application like Microsoft Word. So if I open a Microsoft Word document, I can simply right-click and select paste, and you would have the graphical capture of the TCC as well. You can combine it as part of your report if you wish. This webinar was found useful. At the end, I would like to thank you for your time, your patience, and attention.